see where we stopped. Not here. So we're still on the topic of oscillations in non-conservative systems. So we still did not get to the any physical example, but we need to do more theory in order to understand. So I will recall what we did. So for small oscillations, near the equilibrium, so we consider the variable delta q, which is difference from of our generalized coordinates from the equilibrium. We found the linearized system, which had this form m delta q double dot plus l delta q dot plus kq equals 0, where these are all free matrices m, l, k. And what we found is we know how to solve it. So we know how to solve it. The solution, so we can write a solution. How we do it, we first of all define the larger vector x, which is vector in a phase space, so it's coordinates and velocities. And then we write this equation in the standard form for the ordinary differential equation, x dot equal ax. So A is a matrix which is composed with the matrices. So 0, identity, minus m minus 1 k, minus n minus 1 l. And then solution can be written as a sum over all Jordan chains which we number with I, and then for each I we have this solution which is given by that formula star last time. So it's C1 I put on a superscript. So C1 U1 exponent lambda IT plus the second term was C2 so here it was U1 T plus U2, right? This was the second term and so on. So there, for each Jordan chain you can exponent and so on. So for each Jordan chain you compose this particular solution with arbitrary coefficients, and summing all of them give you general solution. So at least mathematically we can solve it. So before analyzing the properties, let's see what we gain. So we had equation of motion in this kind of Lagrangian form of second order equation, and we can reduce to the first order standard form, and then we just use the standard analysis from linear algebra. So this is convenient because, for example, this is convenient in many cases because the theory for this equation is much more developed than for the previous equation. And the same trick we can do with the nonlinear equation. So let's do the same trick with the nonlinear equations and see that it also give us some convenient formulation. So let's consider original nonlinear system. This original nonlinear system was exactly our Lagrangian equations. and this zero with external force. External force i's component. So this was original system where L, remember the Lagrangian is always the same. This form. So this is rather general expression for the equations of motion. And okay, so what we will do with this? So just recall. So this we can open. We already did it. So when you open, so what happens is that you have this explicit system of equations. So this is when you open equation. Just you put L inside, open this we did last time. Good. So now what is the trick? So we will use exactly the same trick. So we now compose a vector out of the coordinates and velocities. Okay, so now there are no deltas, so we will compose a vector y made of velocities and coordinates and velocities. So it means that we can call velocities by Q capital. That's what I did. So in other words, we introduce a notation, so the Q will be denote Q dot. Yeah. So each component is the velocity. So then what we can do, we can write this equation with less derivatives. So this second derivative here. So what we have, we can write this equation as j equal 1 n mij q, and then it will be q first derivative. And then let me put everything to the left hand side. So we put everything to the left hand side. So we put minus sum. And these are Q capitals. Right? Then there will be minus du dqi and plus q. So in other words, what we have on the right hand side, there are no derivatives anymore. There are no derivatives, so let's just define it as some function. Let's call it f I. So we just denote by fi the full expression. So then what you get is, now you can write this left hand side as just m of q, where m is the matrix with these coefficients, right? By q dot equal f q, where this is vector, so just in vector form. And then you invert matrix. Mass metric is always invertible. Okay, so then let's take this as a second equation and this as a first equation. So we take second equation and first and second equation and form a system. So this equation gives us q dot equal q, and the second equation gives you q dot capital dot is minus 1 q f q. Or we can just write it simpler. So we can just write it as y dot equal f of y. Remember, y is exactly this vector. So y is this vector. And f of y is just defined as, so f of y is this right-hand side. So it's q where q small case and uppercase q are components of y. So we just did the same. So see, it's a bit longer procedure, but same idea. So you take a phase vector which contains coordinates and velocities, just in the same way as we did in linear case. We put coordinates and velocities in a larger vector. And in linear case, we obtained linear system of differential equation in a standard form. And here we obtain a nonlinear system of differential equation in a standard form. So that's just a convenient step. So why it's convenient? Because so it's often convenient for theoretical studies because you're in a standard form. Also, whenever you do numerical simulations, you always will do this, because this is the form of equation, differential equation, for which most of the solvers are formed. So if you have differential equation, you have to transform to this form before you make a numerical simulation. But whenever we consider examples, we will consider them in original form because it's just more convenient. So this is just so there are two equivalent forms of equation of motion. So either the full form of a Lagrange equation, or this reduced standard form, which is nonlinear. Okay, so what we do with this form? So first of all, you can see that easily equilibrium conditions. So essentially, we can have all this. We can write all properties of small oscillations just in this standard form, and this is how the classical theory of ordinary differential equation works. So first equilibrium, which is also called fixed point for equation. So fixed point is a constant solution that does not change in time, and the existence of constant solution is equivalent of, from this equation, of that function f is 0. Correct? So what you can do is that you can make very simple exercise is to show that this condition is equivalent to the condition that internal force plus external force is 0. So remember, for this system, equilibrium condition is that internal force plus external force is 0. For this system, equilibrium condition is f of y is 0. So if you just consider this condition and make and just write it in terms of original functions, you will see that these are just the same. Well, this is the equivalence of this condition is natural because systems are equivalent, and equilibrium condition is equivalent. So then the condition should be also the same. But you can check it directly. You can check directly. Check explicitly. Okay, then the next step is a linearized system. So how you define linearized system for this equation? This is quite rather easy, because what you do, you consider x as a difference between y and y0. Right? Whenever, and you assume it's, that it's small. It's assumed small. So then what you can do, you can expand this function f. So we take function f and consider Taylor expansion. Taylor at point y0. So whenever you take Taylor expansion, so the first term will be f of y0. The second term, so you remember this function of many variables. So the second term will be the Jacobian matrix computed at y equal y0. So remember, so f df dy is a Jacobian matrix, so it's df1 dy1, df1 dy2, df1 2 dy1, df2 dy2, fn yn. So it's the Jacobian matrix. Matrix of all derivatives, for all components with respect to all variables. So this matrix, by the difference, and plus smaller order terms, higher order terms. So now what you have, so this is 0. This is small, so we can neglect it. This is x. So it remains to call, so then what we get, this is x. So what we get is that x dot equal y dot equal f of x. And then what remains is this. So we call this matrix A. And get exactly the same equation. Right? So you can come to the linearized equation directly from the standard form, instead of the first going to a linearized equation in Lagrangian form and then making this transformation to phase space. You can also, just like this exercise, you can also show explicitly. You can show explicitly that the matrix A that we obtain in this way is just the same as the matrix A that we had before. So there's no difference. Because all what we do is equivalent. Just we do it here with phase variable, and here we use with Lagrangian. You did it with Lagrangian variables. So you do whatever you want. The result should be the same. Okay. So now we have nonlinear system, which is you can write in whatever form you want in Lagrangian, in generalized coordinates, or in phase variables. You have linearized system, and linearized system can be solved. So what we can, if we solve a linearized system, what we can say about the original system using this solution, because systems are not the same. Systems are not the same because we neglected a small term. So this term is exactly the difference between the two. We neglected, so the systems are different but very close to each other. So if the system very close to each other, is it sufficient that they have the same properties or not? So that's not so obvious. And this can be, this is a topic which is, for which we have a theory, which is called stability theory. So what we can, the important property in which, how we can relate the two systems, it's the subject of stability theory. Stability. Okay, so first we have to put, say, definition. This is what's called Lyapunov stability. So definition tells that an equilibrium or fixed point y0 of system y dot equal f of y is called stable if, and then there is a mathematical statement that I'll describe. Let's write it and then we see what it does mean. So it means that if for any epsilon positive, there is delta positive such that the difference of the solution to the fixed point is smaller than epsilon for all times if for any and any initial condition which satisfies this inequality. Okay. So what does it mean? So let this y be our variable, probably many dimensional. Just let's assume that they're all in this plane, and here will be time. So what it tells is that whatever epsilon you give, so epsilon is will be our so whatever epsilon of 0, whatever epsilon you give, which is distance. Oh, sorry. So this will be y0. Let's draw it again. So we have equilibrium y0. So what it tells, so whatever epsilon neighborhood you define, right, so which is this distance epsilon from y, you can define the smaller distance which has a size delta. So whatever So whatever initial condition you take in this delta neighborhood, it will never exit the region of size epsilon. So stability means that if I want, I always can be in any small neighborhood of size epsilon around the equilibrium if I take initial conditions sufficiently close to the equilibrium. So I will stay epsilon close to equilibrium if I start delta close to equilibrium. So in a sense that it's stable if I always can control our system near the equilibrium point just by starting sufficiently close. Yeah, and this is just exact formulation how it's done. And so what is important is that it's forever, so it's all times, and for all initial conditions within the delta neighborhood. In other words, if the equilibrium is unstable, it means that for any epsilon, I can start as close as you want and go out. Right? No, there is epsilon, so that I can start as close as I want and get out from the epsilon neighborhood. Okay, so this is the first definition. The second definition is similar. So the second definition is that a stable equilibrium is called asymptotically stable. If, well, I already said that it should be stable, right? But additionally, we have the condition that the limit as time goes to infinity of yt is equilibrium. So this is for any this was for any under the same condition that was in the definition of under the same condition. So essentially, asymptotically stable equilibrium if you have all this what is written here, and additionally, so in addition to this condition, you also have this. So what this means so there is equilibrium, which there is a solution which does not depend on time. And what we claim is that for any epsilon neighborhood, you can define a delta neighborhood. So that whenever you start inside, so first of all, you cannot exit this tube of epsilon size, so you cannot exit. But not only you cannot exit, but you also, at large time, you approach the equilibrium. So that's the definition. So the asymptotically stable is not just that solution doesn't go away, but also it's after large time it re-enters, it becomes equilibrium. Okay. So now what we can do is to see when the systems are stable, asymptotically stable, or unstable.
It became almost a analysis on the line class.
Very good. You see, epsilon delta. Yeah, it's. I knew you will like it. Okay, so let's start with the stability of a linearized system. So what we can say about the stability, so again, let's see that, remember the general solution is that we constructed is that X is the sum of all Jordan chains, so we call them, number them with I, and each Jordan chain gives you a solution as a certain sum. So the first term, then the second term, I put I on the top just to denote which Jordan chain it is. So it's 1t plus u2 exponent, and so on. There are k terms in. So there are as much terms as many generalized eigenvectors in each chain. So what we see, so they're all. So every term that so every term in this solution. So the solution is a sum of terms of generalized eigenvectors, then generalized eigenvectors with coefficients of the form some constant by the power of time, because there will be different powers of time, and by exponent of the eigenvalue by time. So where k is 0, 1, 2. So every term which you have here is of this form. So the constant we can put in the vector. So with these prefactors. Okay, now let's keep constant. You agree, no? So now what we can have for this term. So this term. So what happens with this term? So first, this term, it vanishes. So in other words, goes to 0 as time goes to infinity. If so, let's first of all let's write it. So what it is? So lambda is an eigenvalue which is complex. So let's just write that this is tk exponent sigma t cosine omega t plus I sine omega t, where lambda is omega is sigma real complex part. So you see that whenever a real part of the eigenvalue is smaller than 0, so exponent goes to 0, But exponent goes to 0 always much faster than any power of time. So this power doesn't matter, this term doesn't matter, so only exponent is important. So this term will go to 0 at large times. The second option is this term remains bounded. So its modulus of this term is smaller than some constant at all times. If real part of lambda is 0, so then this is 1. But there can be still oscillations. But we also need k to be 1, to be 0. So this is, in this case, this term, just this prefactor disappears, and then we have just oscillations. Then the next option is this term grows as power law. At large times. If a real part of lambda is 0 and k is bigger than 0. So with a real part is 0, exponent disappears, but there is prefactor which is increasing as a power law, and then there is another factor which is just oscillations. And then finally, this term grows exponentially. If real part of lambda is positive. So if real part of lambda is positive, this is exponent grows exponentially. Also, it has a prefactor which also grows as power law, but at large times, exponent is the most important term. Exponent gives you the largest increase. And then there is prefactor which may oscillate. Okay, so that's the situation. So what you can see is that this, for the stability, these two terms are compatible with stability because they don't grow, because we need to keep solution bounded. So this first and second solution are compatible with stability, but whenever we have third and fourth case, we're certainly unstable because solution cannot stay in the epsilon neighborhood. Solution will certainly go away. Also, there is difference between the first and second case because in the second case we have just the solution is just bounded. So in second case it doesn't decrease. So we just have stability, but not we cannot have asymptotic stability. But in the first case, we can have asymptotic stability. Okay, so this, in fact, gives us a theorem that I'm not essentially proved by this argument, but you need for the formal proof, you need to do some extra work. We will not do it. But anyway, we can formulate the theorem, which is rather clearly follows from these conditions. So the equilibrium, so the theorem has 3 points. A, the equilibrium x equals 0. So remember, x equals 0 is equilibrium of the linear system. When you put x equals 0, it's certainly equilibrium. So that is asymptotically stable if and only if. So what we need for asymptotic stability? We need that every solution will go to 0. So it means that we can only have the solutions where eigenvalue has real part smaller than 0. Is real part of eigenvalues smaller than 0 for all eigenvalues of the matrix A. So this is a full description because we know that it's asymptotically stable if and only if the all eigenvalues has negative real parts. So B. The equilibrium in the same situation is stable if and only if so now for stability we can have either first case or the second. So if and only if real part of eigenvalues are smaller or equal than 0 for all eigenvalues. But we also need we also need that k to be 0. So it means that we cannot have these terms. So that we can only have the eigenvector term. And this is given by this and all eigenvalues with 0 real part are semi-simple. So let's put observation. Remember what means semi-simple. Semi-simple means that algebraic multiplicity is the same as geometric multiplicity. And this means that all Jordan block are degenerate. So it means that all the Jordan blocks are one by one. So there are no Jordan chains. There are only eigenvectors. There are no generalized eigenvectors. So if there is no generalized eigenvector, there is no terms where exponent multiplied by t. Okay, and C is that the equilibrium is unstable in all the other cases, right? So if and only if there is an eigenvalue, there exists at least one eigenvalue with negative real part, with positive real part, or an eigenvalue with 0 real part, which is not semi-simple. So in either case, you do not satisfy the condition B, so you're unstable. So this is the theorem. So this theorem, which is a direct consequence of the general solutions that we got. And the good way to memorize this is geometrical. So we can just plot a picture and see what does it mean. So what we do is we plot complex plane. So this will be real part of eigenvalue, imaginary part of eigenvalue. So the first case A is when the system is asymptotically stable. So for the stability of the asymptotic stability of linear system, all eigenvalues should be with negative real part. So they all should be on the left side. Right? Zero. Just for stability. If you don't, so in that case, when all eigenvalues has negative real part, all solutions at large time just become zero. Right? So that's equilibrium is zero. So whatever, if the system has eigenvalues on left hand side, whatever initial condition you take for the linear system, at large time it goes to zero. So for this, just for stability, the case B. In that case, solution doesn't have to go to zero at large times, but at least it remains. If you start near zero, it remains near zero. So the condition is very similar. You always also have the condition that everything should be on the left-hand side. But you, in principle, allow some eigenvalues to have zero real parts. So some of them can be on imaginary axis, but they necessarily should be semi-simple. So the semi-simple means that there are no generalized eigenvectors, just eigenvectors for these eigenvalues. So then you still have stability. And then the last case is instability. So see, unstable. So for the system be unstable, we need the simple part if we have at least one eigenvalue on the right hand side. Just so there can be some others on the left, but at least one. Or there is another option is that, so let's put it like that. Or another option is that you can have eigenvalue on the imaginary axis, which is not semi-simple. So remember that it has eigenvectors and generalized eigenvectors. So that's it. So that's complete description of the stability of the linear system. And this is our main result that we obtained from a general solution. So we can linearize system, we can find general solution, and by knowing its eigenvalues and eigenvectors, because you need this or generalized eigenvectors, you know if the system is, if this zero, if the equilibrium is asymptotically stable, only stable, unstable. So that's full stability theory, which can be it can be done in complete form for the linearized system. So now the question is when stability of a linearized system or instability so linearized system is x dot equal x implies also instability or stability of original nonlinear system. So remember that how we obtain linear system. We have equilibrium in this system. We linearize near the equilibrium. We can study if this is stable or not. But now there is a warning. So the neglected term. So the difference between the system is just in this small neglected term, right? So this is this. I don't know if it's still here. If it's still here. No, it's not here. So when we made the transformation from first system to the second, we just neglected the small term. So it's small. So it is small. But whenever you study stability, you see you consider large times. So the small term it can have a large effect at large times. So that's a problem. But it can have large effect at large times. So that's important. So when we linearize system, for some times which are not too large, they are close to each other because the difference is really small. But whenever you want to see the stability properties, to see if for long times the system also have a nearby properties, then this is already delicate because we neglected something small, but we want to see if this small term is important or not at very large times. So this gives you okay. So this is just tell that you should be careful, and we will see that there are very many different situations when you have to be careful, and the reason why is this very strong theorem by Lyapunov, which actually make the connection. So it tells you exactly when analyzing this system you can say something about that system. And this we do after the break. No? Okay, so let's formulate this second, the Lyapunov theorem, and unlike the first theorem, it will have just two cases. So this is I will not give a proof because this is a complicated theorem. So you can see theory of ordinary differential equations. So this is one of central theorems in theory of ordinary differential equations. So what it tells that there are two cases. So the first case is if real part is negative for all eigenvalues of the matrix A, then the equilibrium y0 of the nonlinear system is asymptotically stable. Let's write everything. And B, and then interpret. And B, if there is at least an eigenvalue with real part positive, then y0 is unstable. Then let's write it. Then the equilibrium y0 of this nonlinear system is unstable. That's it. So what we have? So first observation is in these both cases we have if, not if and only if. So first difference between linear stability for linear system and stability for the nonlinear system is that here we only have a sufficient condition. Yeah? So here we know that if the system is the equilibrium is asymptotically stable, it's if and only if all real parts are negative. Here the theorem only claims that so if real part is negative for all eigenvalues, we guarantee asymptotic stability, not the vice versa. And in the second case, we also, if at least one eigenvalue is positive, then we guarantee that it's unstable, but also not vice versa. So it can be unstable, but probably some of eigenvalues will be. So that probably there will be no eigenvalues with positive real part, but still be unstable. Yeah, so only sufficient condition, not necessary and sufficient. Okay, and only two cases, A and B. So you see that there is a case which is not covered by this theorem. And in order to see what is not covered, let's put the same graphical representation of what the theorem tells. So the case A, let's call it capital A, then it will be different from another theorem. So on a complex plane, so the case A, which corresponds to asymptotic stability, it requires that all eigenvalues will have negative real parts. So all of them must be here. So if all eigenvalues are on the left-hand side of the complex plane, strictly on the left-hand side, then we know that the nonlinear system will have a stable, asymptotically stable equilibrium. So this is a very strong condition. So because nonlinear system has can have whatever nonlinear terms you have. So whatever this term can be, which we neglected, all what you need is that you linearize, you compute eigenvalues of the matrix A, you see it is all of them are here. You don't care about smaller or higher order terms. Stable, asymptotically stable. And the same in case B. The case B is a situation when so in case B is telling that there should be at least one eigenvalue on the right-hand side. So at least one eigenvalue should be here. But the others can be on the left. It's okay. So you can have, so at least one. And in this case, this is case B, you have instability. So these are two cases which are, so the first case is exactly the case of asymptotic stability for the linear system. So this is a case where both theorems are close to each other. So the situation for asymptotic stability in linear system and nonlinear system have the same form, but not absolutely the same form, because in the linear case it's if and only if, in nonlinear case it's just if. Also the unstable case is similar. So if, but here there are two differences. The first is that, of course, it's if and only if this stays different, but also in the nonlinear case, we only care about eigenvalue with positive real part. What is on a real or on the imaginary axis doesn't help. So the situation where we can really guarantee stability or instability is very similar for the with the stability or instability of a linear system, but not exactly the same. And there is a difference, and the difference corresponds to the special case. So it's special Lyapunov special case. So Lyapunov special case is when you can, in the case where neither A nor B is satisfied. So neither A nor B, and this is a case when the first when the real part of all eigenvalues is smaller or equal than 0 for all eigenvalues, and there is an eigenvalue with real part equal to 0. So this is a special case. So the situation when all eigenvalues are here, but some eigenvalues on the imaginary axis, this gives you special case. So if all eigenvalues are on the left-hand side, but some of them appear on the imaginary cases, this is a special case. And special case is special because we don't have a general automatic condition for the stability. So in that case, stability of equilibrium of nonlinear system actually depends on nonlinear terms. So these terms which we neglected. So this is a situation when the small terms which we neglected actually are important, because they can make systems stable or unstable, irrespective if the linear system was stable or not. So in that case, the information that I get from linear system is not at all important for deciding for if the nonlinear equilibrium is stable or unstable, because everything can be changed by nonlinear terms. And we will see some situation of this. So that's a general theory, and essentially this is it. This is it. So what you have to remember is these pictures. So remember that there is a complete picture for the linear system with complete understanding of stability, and only part of this information is indeed important, because for nonlinear system, which is kind of this original one, only part of the information is important. So it's, we can only guarantee stability if everything on the left-hand side. We can guarantee instability if at least one on the right-hand side. And if some of them are on the imaginary axis, we have special case. So there should be some other method how to deal with the system. And we will also see that how to do. In some cases, you can really study this case, but this already cannot be studied in general. You can just study in some special form of the equations or special cases. And usually this is difficult. So that's it. So this is a general stability theory. So now we go to the, so now we gradually will proceed to specific type of physical systems. So what we do, we will consider linear system. And at the first step, we will make classification of forces. Classification of forces. So remember, so what we did. So we remember that what we had this linearized system, which is non-conservative. And before, and now we will start applying this stability theory depending on for different situations. But it's better to go slowly. So not consider this just a very general case, but rather consider different types of system depending on which forces are included. And for that, I'll give you some, first of all, the plan, and then we will follow this plan. So what is here? So here we have three matrices. So first matrix is a mass matrix. Mass matrix, and we know that it's symmetric positive definite matrix. So then there are two matrices L and K. So what you can always do, so L and K are generally non-symmetric matrices. So we can write any matrix can be decomposed as a sum of asymmetric and antisymmetric. Matrix. So how you do it? So let's do it for matrix L. So matrix L, you can write as a sum of symmetric matrix plus antisymmetric, and you can just write a formula for this. So D is L plus L transposed over 2. And G is L minus L transposed over 2. So first of all, the sum gives L. Then the transpose D is symmetric, because when you transpose, this become L. So it's the same. So D equal dt, symmetric. And the G, if you transpose this, become LT, this is L. So it's just changes the sign. So this is antisymmetric. And of course, you can do the same for the K matrix. So we write K equal C plus N. So C will be K plus K transposed over 2, symmetric. And N will be K minus K transposed over 2, antisymmetric. That's a convenient decomposition. So the form of the equation that we will use is the equation which includes this decomposition. This. And typical origin of the matrices. So where these matrices come? D, G, C, and N. So we already know what C is coming from. Remember that C is coming from the system which is conservative. So when the system is conservative, it's just like this. Right? So C is what's called potential forces. It comes from potential forces. So for the of the conservative system. So the case when the system is conservative, you can write a Lagrangian form of this equation. C is just a matrix of the second derivative of the potential. So that's why it's symmetric. So the physical origin are the elastic forces or gravitational forces. So all the forces which can be written as a gradient of potential, they contribute to C. Now we also know what's D. So D is often comes from a dissipative forces. Remember Q symmetric matrix by velocities. By velocity we already with a minus if you put on the right hand side. It is exactly the model for dissipative forces that we introduced already. Yeah? We already wrote this D by Q dot. It was dissipative forces. So this is and in that case, remember that D was symmetric and positive delta. Okay, then G. G is the usual origin of this is what's called gyroscopic forces, and we will have them. So this is, for example, a Coriolis force in a rotating frame of reference. So usually this matrix G comes from rotation. So if something rotates, exactly the example we'll have, if something rotates, you may, because of rotation, you get this antisymmetric component to the equation of motion. And then n. N is usually called non-conservative. But non-conservative is not that general name because D is also non-conservative. But sometimes it's called circulatory. Circulatory forces. So for example, aerodynamic force. The force of the interaction with the air have this component, which come here. Yeah.
What is Coriolis force?
Coriolis force, what is Coriolis? Do you remember that when you Coriolis force is, remember when you are I don't know how it's called in this. There is this in a park for kids. There is this circular ring where you sit, and it starts rotating. There are two forces. One is a force which you just tries to pull you back, right? So you just sit, and it pulls you back. But then there is another force. So if you try to make a step in the center, what happens if you pull to the side? This is a Coriolis force. So if you sit and then you make you push and start moving. If you start walking in a rotating disk, you start walking to the center, you'll be falling to the side. This is a force which is Coriolis force. So it's exactly you see this is a force which only appears when you move. So you have to you have to walk to the center. If you start walking to the center, you will not, in strongly rotating the disk, you will not be able because something will pull you to the side. And so it depends on velocity. And the fact that it's antisymmetric, it means that the force will be perpendicular to your motion. So that's exactly this. We will just derive it. So that's origin of the. So the antisymmetry is related to the fact that it's perpendicular to your motion, and then the fact that it comes in this term, it's because it depends on, it only acts on a moving body. While centrifugal force will come here. So actually, this splitting has a rather deep physical meaning. So it's different matrices in this splitting. They usually have different meaning from physical point of view. Okay, so now we will have different examples. So I will give different examples coming from the simplest case, which is conservative, and then adding different type of forces, and we will see what happens. And what are the situations, what is the interesting phenomena that you get depending on different forces, depending on different matrices. And using the general theory which we just developed. So the next lectures, they will be simple, I think, because we will, no, not the next, but when we consider examples, they will be simple. And probably more fun. Okay, so what we have is it's a mess. Oh, okay. Okay, so let's consider different situations. Our interest is to consider all of them, so non-conservative situation. But let us start with a conservative. Let us start. We start with a conservative system. we already did this analysis, not complete, but we did this analysis. But we did this analysis before we knew the general theory. So now we kind of recall this analysis, but already we will be based on the general theory of the stability, and so we will see how we can rigorous results, not the results which are proximate. Okay, so the conservative system is when there's external forces was 0. So all forces can be included in the potential. That was a system which is given by all Lagrange equations. And we know that when you linearize near the equilibrium, you get linearized equations of this form. Right? So just only matrix C is there. And C was symmetric because C, which was symmetric because all components were just second derivatives computed at equilibrium. Remember this, no? So this is a. So we kind of made a step back. So no dissipation, no gyroscopic forces, no non-conservative circulation, just this. So the same situation we did. So what we found out. So we found eigenvalues. We knew that eigenvalues, and remember that eigenvalues you can find in this formulation, or you can transform to the matrix A and find it from a standard formulation. And this will be just the same thing. So eigenvalues are given by the determinant. And what we know is that all eigenvalues, which are n of them, all squared eigenvalues are real. This we found. Okay, so we can apply this theorem. So if there exists an eigenvalue which is positive, which is square of it is positive, right? Let's say equal sigma square, which is positive. Then the original eigenvalue is square root, which is taken with both sides. Then lambda, which is taken with plus sigma, is bigger than 0. So real part of lambda, which is the same as sigma, is bigger than 0. So real part is bigger than 0. And we're in this situation. Q0 is unstable. So by studying this system, we know the stability of that system. The example is, for example, the inverted pendulum. The gravity. So if you compute eigenvalue here, this is what we did. Eigenvalue will be positive. We did this. And we guarantee that whatever nonlinear terms you put, this upper position will be unstable. So this position is unstable. It all is false. So this is somehow this is a rigorous proof that the position upper position of the equilibrium is unstable, because we found eigenvalue. One of the eigenvalues has positive real part. We apply Lyapunov theorem. Done. Let's see if we can prove the rest. If we can prove that the lower equilibrium is stable. And it turns out that it's much more complicated. So we can only hope on the stability if there are no such eigenvalues, right? So otherwise, all lambda squared should be smaller or equal to 0. Let's write it. No, equal to 0, or make it negative. All of them. Because if any, because here we just assume that just at least one is like this. So the opposite case is that all of them either 0 or negative, which means that when you take a square root, is that lambda is 0 or is purely imaginary. So we are on a special case. So all eigenvalues stay on the imaginary axis, so we have a special Lyapunov special case. So that's bad. So you see that all conservative cases are not covered by Lyapunov theorem. And we need to study this system separately. And this is what we do. So the question is, so this means somehow that we don't have so far we don't have a theory which proves that the vertical position is stable. So why it's stable? Linearized system is stable. For linearized system, it is stable, but linearized system, but since it's a special case, we cannot say that that it will be stable for when we take into account all the nonlinear terms. So here we have a theorem that we will prove. We will just start it now. So we can prove, and this you will see that it's already a different way how you prove stability. So this is a spectral way, because the eigenvalues is this set of eigenvalues is called spectrum. So this is a spectral way, and we will need to find another way how to prove. And theorem will tell is just so if all eigenvalues satisfy such that their squares is strictly negative, so this case, then the equilibrium of nonlinear system is stable. And here it's not asymptotically. So let's make it as an observation. So that's theorem that we have to prove. So we want to say that even if we have a special case, if all eigenvalues stay on the imaginary axis, but not at 0. So we only exclude 0. If they all stay in the imaginary axis, we we still guarantee stability. So this will guarantee that if we prove this theorem, we prove that the normal vertical position of equilibrium of pendulum is stable. For pendulum, it's easy, but for slightly more complicated system, it's already not that easy. Well, even for pendulums. Okay, so let's prove this theorem. So for this theorem, a couple of pages of proof. So I first just prove some properties. Let's prove some properties of this theorem. So first proposition is, let us prove that if, so that all eigenvalues are negative, all squares of eigenvalues are negative if and only if symmetric is positive definite. So let's we show that this condition from the theorem is equivalent to asking that C, which is symmetric matrix, is positive definite. So let's prove this. So remember, C positive definite means that for any vector V, this is bigger than 0 for any vector V which is not 0. This is what this means, and this is equivalent to asking that all eigenvalues have negative squares. Okay, so how you prove it? So proof is the following. So let's consider all eigenvalues. So all squares. So they are all negative, right? By this condition. Okay, let's just consider arbitrary. So let's consider all eigenvalues with corresponding eigenvectors. We already proved that all of them are real. So from the theory of linear algebra, linear algebra guaranteed that we can select eigenvectors such that UIT M Uj equal delta Ij, which is Kronecker delta. So it's 1 when I is j and 0 when I is not j. So when they are orthogonal. And if you remember that this was your exercise. So your exercise, you already guarantee that whenever lambdas are different, this is true. So this is 0. So the linear algebra also guaranteed that you can choose eigenvector even if lambdas are the same to be of this form. So this is we just borrow this result from linear algebra. And now what you can do, so this means that in particular, so that U1, Un is a basis. In Rn. Also result from a linear algebra. So we can choose basis in Rn with eigenvectors which satisfy this condition. And then we can take vector v, arbitrary vector v, as a linear combination with arbitrary coefficients. Right. So now with this vector v, we'll check this condition. So what is v TCV? HV is a sum. Sum can be put outside. It will be CI UI transposed by C UG, and then it will be CJ UJ CJ UJ, like this. So this is V, this is VT, this is V with a sum. And this gives you, so coefficients can be put outside. But now remember that what means eigenvector. So it's eigenvector satisfies equation lambda I squared. Let's put J. M plus C Uj equals 0. This is the equation for the eigenvector. That means that C Uj equal minus lambda J squared M Uj. So we can put it here. So what we get is Ij from 1 to n, Ci, Cj, Ui, T, and then this minus lambda J squared MUJ. Okay, let's put all the coefficients outside. This will be minus Ci, Cj, lambda J squared, Ui, T, M, Uj, and this is Kronecker delta by the choice of eigenvectors. So it means that it's a sum when I equal j. So what we found is that Vt CVT is a sum with a minus Ci squared lambda I squared. So now, if all lambda I squared are negative, you see this is always positive. So we proved that if this is true, C is positive definite. Now is backwards. If C is positive definite, then this should be true. But this is positive. This is positive only for any coefficient, only if all lambda squared are negative. You get to this condition. So this is if and only if. So now we can rewrite this theorem and write a corollary. Which uses proposition that if the C matrix is positive definite, then the equilibrium Q0 is stable. So either you check all eigenvalues or you check just positive definites of C. And and the last thing before going to proving the theorem, which we do tomorrow, we just see what means C positive definite physically. And for understanding what is physical meaning, we compute energy. So remember, there is energy. Energy for the system, which was here, is energy can be written as, let's already write it in the matrix form. Delta 1/2 Q dot transposed M of Q dot minus U of Q plus. So potential and kinetic energy plus potential energy. So this is just matrix form of writing this sum. Right, so that's. So what do we have from this? So now remember that C is so what do we have? So U of Q expanded in the Taylor series was U at Q0 plus linear terms and this was 0 because of equilibrium. So this is equilibrium condition. And then the next term was symmetrics. And then higher order terms. So when you put it back, what you see for the energy is energy will be this constant term, so E0. So we call this E0. Plus this. Plus that. Plus smaller order terms. So this is positive. And this is positive if the matrices are positive definite. So it means that energy has a local minimum at the point Q0, Q0, and Q dot equals 0. So essentially what we ask for in the theorem and what we will use for the proof is that energy has a minimum. So and this is what we will prove. So we will essentially prove that whenever energy has a minimum at the equilibrium for the conservative system, because conservative system is defined by constant energy. So in the motion, energy doesn't move. If the energy has at equilibrium has a minimum, strictly local minimum, we have stability. Right? So this is the property which helps you to prove stability, even though we're in a special case of Lyapunov. Okay, so this is what we do tomorrow. And then we continue to other systems, which are non-conservative. That's it.